Hey guys, welcome to another episode of Robo Papers. Super happy today to have a pretty big team. All of them co-authors from this paper called Humanoid Everyday, a comprehensive robotic data set for open world humanoid manipulation. So we have here today Zhenyu, Jiageng, Xiawei, Wang, and Hongyi. Maybe as a start, maybe Wang, you can start first, and then each of you can share a little bit about yourself before we dive into the paper.
Yeah, sure. Hello, everyone. My name is Wang, and I'm an assistant professor at the University of Southern California, leading a robotic lab here. So at the USC, we are doing everything related to 3D computer vision and robotics. We try to leverage AI to solve daily robotic tasks, so that we can augment the human intelligence. We can solve some society problems with improved robotic algorithms with better robots. So that is what we're doing. And joining me are my students, Zhenyu, Jiageng, Xiawei, and Hongyi, who are the leading authors of this Humanoid Everyday project. So they basically did all the heavy lifting work of this project. So I will let them to introduce themselves.
Yeah, my name is Zhao. I'm a senior undergraduate student here at USC studying computer science.
Hongyi, you want to introduce yourself?
Yeah. Hi, everyone. My name is Hongyi Jing, and I'm a master's student in computer science in USC. And I'm really happy to introduce our work, Humanoid Everyday, here today.
Hi everyone, my name is Xiawei, and I'm also a senior undergrad right now at USC studying computer engineering and computer science.
Hello everyone, my name is Jiageng. I'm a PhD student advised by Professor Wang. I'm happy to be here to present our work, Humanoid Everyday. I'm happy to discuss everything about robot manipulations, humanoids, robotic controls, and others. Thank you.
Okay, very cool. Yeah, so maybe Zhenyu, I think you can start. I know you have this presentation to go through with us.
Yeah. So here we present Humanoid Everyday, which is a comprehensive open world data set for humanoid robot learning. So, and in this data set, we have over 10.3K trajectories, over 3 million frames, and 260 tasks, all taken using the Unitree G1 and H1. And these tasks include 7 categories, like basic manipulation, deformable manipulation, tool use, articulated manipulation, high precision manipulation, human-robot interaction, and local manipulation. And you can see, you can get a little preview of what some of the tasks that we do that are contained in our data set. But yeah, all of these are like high-frequency teleoperated data that we collected manually. In order to enable this data set, we first made huge improvement of the original data collection pipeline offered by the Unitree team. They released this open XR teleoperation system like earlier, I think in the beginning of this year. But then it was a little bit too slow, and in areas such as like collecting large stream of data. For example, we have a lot of modalities here. We have the depth, the LiDAR, the RGB, and the tactile sensors, and some of the proprioceptions. So all of these have to be taken in synchronous. So to enable that, we rewrote a lot of the data collection pipeline. So here you can get the basic overview of what our data collection pipeline is doing. So it takes wrist poses from an Apple Vision Pro that the teleoperator wears. And so the Vision Pro tracks the hand poses and then transfer them to a viewer server, which is like a WebSocket server that gets the VR data, and using that VR data we can do IK solving, and then we get the joint poses for the humanoid robots. And after this process, we have already collected the action that we want to store in the output data streams. And in the meantime, we also have the robot that's streaming, egocentric view to the teleoperator, also through this viewer. And we have also another, we also have the ego view collected here. And also we have the LiDAR server that's separate, and some of the proprioception stuff that's already internally enabled by the Unitree robots. And all these streams of data are like collected independently, and however, they're also all synchronized at 30 hertz. We do that through the use of by leveraging Python shared memory, and then we were able to like create different processes, like separate processes for each of the stream, and we were able to collect them synchronously. Yeah, and also we have this data viewer, and I believe Xiawei can jump in and talk a little bit more about this.
Yeah, sure. So, in order for users to really know what data we have and be able to, scan through different categories of data and see which one they could use, we made a data viewer that has a selected 50 tasks from the 7 categories, and each of the tasks would have a text description, a third view video, an egocentric video, and also point cloud and depth visualization at the bottom. Yeah.
Yeah, so after collecting all this humanoid everyday data, we then decide to train some policies, including like imitation learning methods and the VOA models to test if our data can support our Unitree G1 robot to do this manipulation tasks. So you can see here all these videos. They are all the examples of our autonomous policies on this humanoid robots. And so these videos, they all represent like different categories in our data. Like the first one is rotating the chair, which is the articulated manipulation. The second one is to folding this towel, which is the deformable manipulation. And the third one is inserting the flower into the vase, which is the high precision task. And then the robot comes closer to the door and tries to grab the handle, and we make this the local manipulation task. And the fifth one, the robot just tries to use the eraser to erase this task, and we call this the tool use task. And the final one, it is like a person hands over the dumpling toy to the robot, and the robot then takes it and places it on the desk. And we would limit the human-robot interaction task. And Zhenyu, can you go to the next slide? Yeah. So we then test all these imitation learning methods on these 7 task categories, and we run this benchmark, and the results are shown here. And first of all, we can see that on average, all these VOA models with pre-trained priors, they outperform all those imitation learning policies like the OpenVOA, the OpenPy policies, and the GROOT policies. They all have a better performance than the traditional imitation learning ones, like the DP, DP3, and the ACT ones here. And also, we found that the GROOT N1.5 is the best policy among all these imitation learning methods, because we think that the GROOT N1.5 is first pre-trained on a lot of humanoid data, and we think such a humanoid pre-trained prior can give us much more valuable information and can help us in this robot learning. And finally, we found that like all the policies actually perform very poorly on those high difficulty manipulation tasks, like the high precision task here, which is inserting the rows into the vase. And we can see that only OpenVOA have a success rate with only like a 10% success rate here. So we found that this is we can. I think right now for the manipulation task in humanoid, we think there is still a lot of difficulty to find a really successful method here to solve this problem. Yeah.
I had a question about this. So I know this isn't exactly what your work is about, but like, why do you think GROOT endpoint 1.5 did the best? Do you have an intuition? Like, what is it? What it's trained on, or any ideas?
You mean why would you rethink the GRUD 1.5
Yeah,
is
why?
the
What's
best
the
one?
intuition for why is
Yeah,
GRUD
because you
performing
can see
better
here
than?
on average, the GRUD 1.5 actually achieves a 51% success
Yeah.
rate, which is the highest among all these methods. Yeah, and I think the intuition is just like because it uses a large pre-trained data from the humanoid data collected from the NVIDIA, and we think that these humanoid pre-trained priors can actually outperform other priors like collected from the robot arms and like others because we are
So-
doing this training in the humanoid setting. Yeah.
So it's because the Pi 0.5 robot is less like your robot, basically.
Yeah,
That's
because
why.
they
Yeah.
actually they are pre-trained on a large data from the robot arms, and which is only has like 7 action dimensions. But in our humanoid settings, actually the humanoid has an action dimension of like 28, which is rather different from the robot arms. Yeah.
Yeah, actually, I have yeah. Before you move on to the eval
Yeah.
part, yeah, I have so many questions, right? So, I guess firstly, how many G1s did you break in the process of doing all this? It sounds like, yeah, like, how many G1s, and I guess also like how long did it take for you guys to collect all this data? It sounds like a Herculean effort.
Yeah, because 3
yeah.
million frames is like 30 hours of data. That must have taken like a really, right? Is that, sorry.
Yeah.
Go. Yeah.
Yeah, I
It's a
mean,
good
it's a
question.
huge effort. So we started this project early January, and has been almost 9 months to finish the whole data collection and the model training, everything with a couple of students with Zhenyu, Hongyi, Xiawei, who were like fully committed to the project. And also we hired additional students to help us collect the data. We spent lots of time on this, and in terms of number of G1s we broke, I guess, 2 G1s, and Unitree was kind enough to help us fix them and or to exchange the G1 for us. Yeah, that was a lot of heavy lifting scene behind the scene.
It's not so bad, actually. It's pretty good.
So I guess in terms of just an absolute number of hours, if you were to count by hours, is it like what Chris say? Maybe you mentioned this already, but is it something like tens of hours? Is that the data set size now? I know it's very diverse across many categories.
How many hours do you have? Do you have
Yeah,
a
I
rough?
think we have like probably like hundreds of hours, yeah, at least, to collect all the data.
Well, so I guess there are 2 numbers here, right? One is the number of hours that is, in your published data sets. And then I guess that's the second question, which is how many actual hours, man hours has been put into Teleop. So those are 2 different things, always, typically, So I think firstly, like how much is it in this data set,
So in total, we have like 3 million frames, and it's taken at 30 hertz. So like 3 million. If you do the math, it's 3 million divided by 30.
It's about 30 hours, I think. Right? Yeah, that's what I was doing the math for.
I see. So 30 hours. So and then I guess it's around 30 hours. I just asked ChatGPT. It's around 30 hours. But that's of course like very 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 diverse, very clean. Like all these modalities that you guys have. It sounds like you guys took 9 months. So what would you say if you were to guess? Like I don't know whether you guys even track that. Like how many hours did it take for you guys to actually do the teleoperation in order to get this very precious, let's say 30 hours, which is still a lot to be honest in my view. But I'm just curious how many hours did it take you guys to do that?
Yeah, go ahead.
Yeah, so I think because we have 260 tasks, and usually each task would take around under 30 minutes, or really if we're doing high precision manipulation or locomotion, it would be like over 30 minutes, maybe 40 minutes for 40 episodes. So basically, if we do the math, let's take an average, maybe 35 minutes times 260 tasks, 9,100 minutes divided by 60, 151 hours. If we can't do it like really 24 hours a day, so if we do it like 4-5 hours a day, it's 30 days. But in reality, the 30 days are if we were to have like all the materials and all the outlines of task ready and we just do it one by one, but in reality, we spend a lot of time really optimizing which task we're doing, and we take a lot of times, really developing the task so that it ensures training quality, because we don't want too difficult task or too impossible task that has random, like too much randomness. So yeah, we really spend a lot of time doing the planning of tasks. Yeah.
Right.
Makes sense.
And
Cool.
as Xiawei mentioned, so doing the task maybe only take a couple of 100 hours, less than 200 hours. But a lot of time we need to design the task, and also we need to redo a lot of tasks if the data quality is not high. And also, when we have different people collecting the data, the quality is hard to control. So we need to do a lot of quality control, quality assurance afterward, after we see the data. So that actually takes much more much more time. And at the same time, a lot of time when we broke the robot, or when something happens with the finger or with the arms, fixing those hardwares also took a lot of time. So that's why the project took almost 9 months to finish.
Yeah.
And
Yeah.
also, when we train the policy, and we found that some tasks are hard to learn and some tasks are easier to learn, and we may need to rethink the task, and we may need to recollect the data. So coupling everything together, that takes a very long time.
Yeah, completely understand. Yeah, I guess like yeah, because you guys started in earlier this year. I mean, I would say even now, like whole body teleop is still, it's still not solved, right? It's still very
Right.
much research papers. Chris and I
Right.
have interviewed many authors. I'm
Right.
curious, like just having decent whole body teleop in order for you to collect the data in the first place is non-trivial. Like what kind of like whole body teleop do you guys using? I don't know. Have something internal, or use one of these I don't know, maybe clone or twist, or what do you guys end up using when you
So
do the actual teleop?
Yeah, so we developed the VR-based, Vision Pro-based teleop. As Hongyi mentioned at the beginning, so we try to speed up the teleoperation. We try to have a real-time teleoperation. But of course, at that time, there are still some limitations. For example, it's hard to control the pelvis and also the legs together, because there are multiple degrees freedoms in the same axis. So we didn't take care of that. But right now, as you know, there are very recently there are many great teleoperation system coming out, like the Twister 2, or the one that was just released
Sonic
by Unitree. Yeah, Sonic is another one.
and then
today.
Unitree as well. Yeah.
Unitree has a one. I think Unitree hasn't really open source their code. And also today, NVIDIA released Sonic. But still, I would say teleop is, as you mentioned, is not a solved problem. It's still quite hard. And also, if you want to add the dextral hands to teleoperation, so that is even harder. And we don't have a good device or a combination of multiple devices to really capture the whole body vision, whole body motion with the dextral hands, with everything.
So, am I right to say that right now the way you do it is using some kind of VR headset, but then the teleoperator just put it on the neck? And then it's mostly whole body, upper body, and then the lower body, the navigation is using some kind of joystick. It's a kind of policy, right? Okay,
Right. Yeah. The lower body is a user of the shelf for Unitree's policy.
I'm also curious to ask a follow up. You mentioned something about you guys did a lot of like so-called data cleaning. What are the factors that you consider when you say, okay, this is not a good enough data collection? Like what do you look for? When you look at an episode, okay, this is not good enough, going to redo again.
Yeah, so initially, our data collection pipeline, there were like some little bugs because we have so many modalities. So sometimes when we were working on, just taking the data, we like at the time during the process, we didn't really pay much attention to what we didn't like examine each episode after we've taken them. So for example, sometimes when we didn't like gracefully shut down the previous data collection, there were like like some like resource leakage due to the fact that we used shared memories. So it could cause sometimes maybe like the depth was not being recorded. So we had to like redo the whole episode or even the whole task if that was also sometimes the camera view, the ego view does not see the hands really well.
Yeah.
For example, some tasks I think that's also one of the limitations of the G1 robot because the real
It does
sense
have an actuator neck.
use has a very narrow field of view. So a lot of times when we like extend the arms to grab something that's far away, the camera does not really see it that far, and we had to like also get rid of those.
I see.
About how much? So, and then also there's like operator error, like mistakes.
Yeah, exactly.
About how much data did you collect versus include in the data set? If you know the answer to that.
We got rid of a lot of them. I think maybe Xiawei can answer that.
Yeah, I think the main data that we abandoned were at the beginning of the project. I would say maybe around 20 to 30% of the data we abandoned them because they were useless data with wrong timestamps or even wrong frames. And but that was mainly just at the beginning. But later on, when we started to have some experience with data collection, we would actually plan it out. Like before we start taking the video, for example, me as the teleoperator, I would be thinking, oh, if we're doing this task called inserting a flower into the vase, it means that we need to pick up the flower and insert it. And since the G1's robot has very narrow field of view, I need to be aware that when I'm taking the data, I need to ensure the flower doesn't get out of the field of view, the camera view. So to ensure the data quality. So basically, it really is like a experience-based tasks. So it requires the operator to know what they're doing from the robot's perspective, but not from their own eyes perspective. So
Makes sense.
Yeah,
Okay,
I'm curious.
on that task.
Yes,
Yeah,
sorry,
yeah.
Chris.
Oh, it's just because he was mentioning the vase task. I was going to ask, like, what was your success rate, Xiawei, at that? Because the models all really struggled at it.
For human, because we really optimized the teleoperation pipeline, so we could do very high precision tasks. Because if we are just not moving our head and just moving our hands, then the success rate would be around 80%, I would say. Yeah.
And I guess you mentioned about a lot of it is hinges on kind of the skills of the teleoperator. How's the actual experience for you guys? I imagine each of you put in hours of like teleoperating, right? How is it like? Like, is it really the case that, or rather, how many hours of training or practice does it before you guys feel that you are actually maximizing, like pushing to the limit of what your whole body teleop stack can do?
I would say for teleoperators, there's a few tricks that someone could get really hands-on really fast once they know it. Basically, maybe I would say a good 2 hour, under 2 hours of training would help students to get hands-on with teleoperating. Because the really hard part with teleoperating is that since the G1's neck couldn't move, students needs to make sure that their neck doesn't move, because if their hands are at the same place, if they move their neck, for G1, their hands would be moving to the other direction that the head is moving. So Yeah, it's really tough for students to not move their neck when they're teleoperating because if they want to grab something, for example, on the right side of the desk, they would intentionally just like, rotate their neck, and it's really hard for them to adapt to it at first. But after 1 hour or 2 hours of training and teleoperating, they would be getting used to it. Yeah.
How do you guys think about the different additional sensors that you guys put? Right, I noticed you guys also have a third person exocentric view, and then you put some lidar. Could you talk about like that process? How do you think about what modalities to collect, why they're useful, and things like that?
So here we for the lidar, it's really all baked into the G1 system. We were just trying to maximize all the modalities that we can take out of the G1 and the H1. So they both have the lidar, at their head.
I see. And I suppose like so you guys did so much work to gather this data set, and then you guys then do this like actual testing as you show in this slide here. How has the data set like affected these results in your view? Is there anything surprising that you didn't expect?
Yeah, so I think first of all, we found that all the traditional imitation learning methods are not working well on the majority of our humanoid data, and we first think that we do not collect the correct data. Maybe the data quality is not that high. So we then try to like collect more accurate data, and we then train with the same imitation learning methods, but we still find out that maybe this imitation learning method just cannot work well on this humanoid data set. So then when we turn to train all those large VOA models, we found that wow, this open VOA actually works very well on the humanoid manipulation. And then we try to tune the the open pi methods like the pi 0.5 here and the pi 0.5 model here, and we also find that well, actually, the robot can do the manipulation task very well compared to the imitation learning methods. And finally, when we try to train these GRUD models here, we find that the NVIDIA GRUD model is the best among all these VOA models. And yeah, I think that's what we are getting from this training process.
I'm curious, did you have some ablation study where you do this like just straight out the box, like can GRUD or Pi do any of these?
Yeah, actually we do some ablation study here, and Zhenyu, can you like switch it to the paper so we can talk about it? Yeah. So you can see here. So we do this. So in this ablation experiment, we want to validate that our humanoid everyday data is really useful. Can serve as a useful prior in training those VOA models. So actually, when tuning those VOA models, we do this ablation study. The first baseline is that we directly tune this like I'll say like open VOA, direct tune it with a new task like inserting the rows into the vase. And the second choice is to first tune this open VOA model with all the humanoid everyday data like 260 tasks, and then tune it with this inserting the rows into the vase task. So comparing these two methods we can see that when pre-trained first with our humanoid everyday prior, we can see that our the whole performance is actually better than the one without our humanoid everyday prior. So yeah, you can see it here. Like for the pi 0.5 model, if without the humanoid everyday prior, we can never get any success rate in this task. But with our humanoid everyday prior, we can achieve actually 4 out of 10 to succeed in this task. And actually for all these VOA models, we all find the same, yeah.
I see. Yeah, this is really awesome. I mean, it clearly moves the needle. I think it does make sense, but I think the question always is, I guess how much data is needed, and I mean, clearly getting even this 38 hours took months of hard work, but then it clearly does move the needle, right?
It sounds like the next 30 hours would be faster if you wanted to. Hopefully other people pick up the torch, I guess. So do some. because you guys used a pretty off-the-shelf Jiguan, right? Like it's the Uni tree grippers, like no custom hardware.
Yeah.
That's great because it means that other labs can more easily participate and test stuff, and I think it's
Yeah.
it's a really nice step, really nice decision. I think. I did want to
think
ask about that.
Sorry, Chris. Yeah.
Yeah, because you collected all this depth data, and I'm sure that you have plans on this one, but why? Like none of these methods here take advantage of that at all, right? Like none of them take advantage of the lidar or the touch sensors. Maybe DP3, but like they don't. Right. So do you have any thoughts on that? Like, is there anything that do you think that you could do better by including that extra information?
Yeah, so actually we do try like introducing the tactile sensors into our training process, but it turns out that it's not working very well because so for the G1 hand, the tactile sensor has a dimension about 66 dimension. So but for the humanoid robot, actually the action dimension is only 28. So actually 28 is really large for a VOA model compared to those robot arms. And if we add this, the tactile dimension into it, it's nearly 100 action dimension. So that's really difficult for us to train on those VOA models. So actually later on, we want to solve this problem by introducing the action tokenizer. We can actually tokenize for example, for a horizon of for a horizon of 6 by 28 humanoid action horizon, we can tokenize it into only 20 tokens. So in this way, it would be easier for the VOA models to output the correct humanoid actions. And we are still trying on this method, and hopefully we can get some better results in the future. But that's our future directions in this. Yeah.
Exciting. Cool. But I'm sorry, why would the tactile sensor increase the action dimension?
Yeah, because actually if you are doing the prediction, so the input should be the first is the humanoid robot action horizon, which is 28, and you have to also include the 66 tactile sensors into your model. And I'll say, actually, in the VOA models, I think it's better to have the input and the output have the same dimension. And so if you exclude the tactile dimension from the output, I think we found that it's actually not working. Yeah.
So to some extent, it's an architectural limitation. So is that?
Yeah.
Okay. Yeah, that makes sense.
Yeah, but I think it does make sense to me that you guys, if you guys are going all the work to do the teleop, might as well just collect the tactile and a couple more modalities if you can. Eventually, the algorithm will catch up and make full use of these. So I'm glad you guys just did that anyway. Someone in the community can figure that out. But actually, maybe that's a good segue. I know you guys have this really cool thing you guys want to maybe open up to the community as well. Some kind of eval as a service in the real world. Do you guys want to talk about that? I know that's the next slide. Yeah. Oh, yeah.
Yeah, so we made this cloud evaluation platform basically because we think that most of the researchers right now, even though they could train models and get data on their computer running, but it's really hard for them to get hands-on with real hardware. For example, the real G1 robot, because the cost is really expensive and there's limited access to it. So we made this website so that the user could train their model on their own computer and connect to our server through a proxy server using the server IP and port. And then basically it becomes a back and forth sending with their inferenced action and our picture and the robot state. Basically, we would send the RGB image, depth view, and robot state to the user, and the client would use these informations to do inference and send us back the next action that they want the robot to perform. And we've done a lot of local tests right here in our lab, and it turns out to be performing pretty good with connection, and it has a a strong connection for user and client, because so that we doesn't lose important frames. Yeah.
So what you're doing here, what you say is that the actual inference, is it done? I mean, is it done on someone else, GPU in the cloud, or
Yes.
are you downloading? Oh, I see. Wow, that's crazy.
Yeah.
So
Yeah. And we are actually planning on updating this so that in the future, the user could just send us a checkpoint that they created, and then we will just use that checkpoint to do local inference here. So it would be much more easier for the user, and we could actually be more flexible with when we'll be performing the experiments. And Professor Wang also mentioned that we might be hosting a challenge with this website, so user would just train their own model and using our data sets, and we will be performing the checkpoints and see which trained model outperforms the others and give them a award. And yeah.
I love this. I don't know whether you guys know of this other project called Robo Arena. Yeah, but I guess you guys are doing humanoid, which I think is potentially a lot more difficult operationally.
Yeah.
I'm curious, like, about the cloud inference part. Because I mean, definitely once you do it through the cloud, there have to be some latency. I wonder, given that there's so many DOF in a humanoid, like, what is the limit of the type of task that you can still, reasonably, expect the policy to be able to do? Maybe the policy could do more, but it's just that the latency is just there, and therefore it can't do more. Like, how do you guys think about that? You see what I'm saying? So imagine if someone have let's say a very, very capable policy, supposedly, but then if you give that, if there's any latency, the latency compound, right? Because ideally you want to stream everything 30, and then literally in ideally zero latency, then it will be the full capability of the policy. So I wonder, in your testing here, when you do like having some of this policy in the cloud, is it, for example, is it only doing simpler like desktop manipulation tasks, or can it really do the full suite of things a full humanoid can do?
So I think ideally we can do some local manipulation tasks, but with controlled environments. So again, we want to unify the evaluation, and we want to make sure the evaluation is fair and reproducible. So that's why we still need to have this controlled, confined lab environments. We want to make sure the evaluation is fair and reproducible. So we need this controlled, confined lab environments. So we need to design a certain number of tasks, and we hope the tasks can be like hard enough for some local manipulation tasks. And that is our ultimate goal. For open world evaluation, I think that's a stretch goal for the future, which is probably the ideal case for all the humanoid evaluation or algorithm evaluation tasks.
Yeah, I mean, I imagine it's non-trivial, especially with this. Yeah, but I'm very glad you guys are even trying this. It's I mean, me and Chris talk about this all the time. We lack benchmarks. We lack, like, more like a neutral eval, real world eval especially. So but I can imagine why this is a natural next step, because you guys did all the work doing the teleop. Doing eval, it's a natural thing to do next as well.
So in our humanoid everyday work, actually for the local manipulation task, we only include the very simple high-level lower body movement, such as like making the robot moving forward or turning around. But actually, finally, we want to train some generalizable whole body policies for more expressive local manipulation tasks. And so, like you can see here, this is the data we collected recently, and we developed our collection pipeline to be this expressive whole body movement, like the robot will actually first pick up the dumpling point and then crouches and to place this dumpling on the chair and then stand up. Yeah, so in the future we want to train our all the VLA models and maybe develop some more newer models and to see if we can train some really generalizable policies on this whole body local manipulation tasks.
Does that mean we should all look forward to like a Humanoid Everyday 2 next year with full body manipulation?
Yeah.
Okay.
Yeah, this is awesome, man. I suppose this is the last slide, is it?
Yeah.
Yeah.
Yeah. Yeah, I guess, I mean, maybe you guys already kind of alluded to a couple of these, like, but I'm curious, like, if you were to sum up the last maybe 9 months of doing this, like, what are some of the, like, maybe surprises and maybe main takeaways that, you know, people reading your paper should also get, I mean, basically learn from your experience. Like, what would you say are some of the very key takeaways, especially if they're surprising to you? Yeah.
Yeah, we were really surprised that how like you know, sometimes the diffusion policies from our experience, we found that diffusion policy did not work as well as the diffusion policy 3D. So using depth as the one of the states, the observation, actually works better than having just raw RGB image. Yeah, I think that's very interesting.
Yeah, my personal experience when working with students and when observing how they work on this project is that teleoperation is still quite hard and it's not scalable at all. And we definitely need other source of data to scale up robotics, to solve robotics. So as you saw from journalist blog post a couple of days ago, so they use UMI style data to scale up robotics, to scale up manipulation. So I think we want more of those work to really scale up robotics with egocentric video, with some egocentric human operations that can be transferred to the robotic space, that can be used for pre-training the robotic policy models. And with that being said, teleoperation is still quite important. We still need teleoperation for post-training, for alignment to the robotic action space. But I guess the data scale compared to large-scale human operation will be much smaller. And also, in addition to this different source of data, we need simulation for evaluation, for data augmentation, and also we need generative models for data augmentation and other things. So in summary, my personal lesson is that as of now, we still see very small of humanoid data available. So we are still quite early in the process, in the journey. So we definitely need to solve the data problems for robotics, then we can solve robotics.
Cool. Anything from Xiawei and Hongyi?
Yeah, so actually I think that when we are doing this humanoid everyday work, like I mentioned here, we only use this the high level simple, you know, lower body movement. So but when we collect this data, like when we include some more complex movement like crouching, like standing or sitting, and even maybe jumping in the future. So we find that actually it's getting much more harder for the current VOA models to train these policies. And we found that like during inference, the robot is doing some random movements, especially in its lower body. Like in this frame, it's still standing, but in the next frame, it suddenly falls and like sits on the ground. So I think this is also another work we can further optimize in the future. And I think the current existing frameworks cannot solve this problem very well. So maybe we can do some optimizations and solve this in the near future. Yeah.
Yeah, I think for me, because I did most of the teleoperation parts, and I felt that companies right now are more suitable for doing humanoid research and training right now because they have the money and they have the power and people to do all those data collection. So I would say that for researchers right now, the best direction is to develop actually, whole body data collection pipeline, or to develop policies on top of the data sets that company can train. Because I felt when we are taking the data, um, it's really hard for labs and research centers to do all these works. Even though we were able to complete this, we took a long time, a lot of commitment to this project, and I felt that companies could, if companies could do more data collection in this industry, this humanoid industry would definitely progress faster, and researchers would be able to perform better research, and eventually a more robust and sophisticated system with humanoids.
I'm guessing this is a request for companies to share more data publicly. Is that the?
Yeah.
Yeah. Makes sense. It's a good question.
Yeah. Good request. Maybe Jiageng as well.
Yeah, I actually believe in the power of in-the-wild teachings because it's very hard to scale up the physical robot. So basically, every of the teleoperation tools, they need a physical robot with a human, and so you have to. The manufacturing of the physical robot is limited by the manufacturers, but the humans' labors, it can be crowdsourced, or they can be more scalable than those you teleoperate with physical robots. So I'm more interested in how do you apply those in the wild. One dimension is how do you apply those in the wild data, especially you're using like egocentric manipulation, human manipulation videos to train your humanoid robots. So that is one thing I'm thinking about. And another thing is so how do you design like exoskeletons, just like Wumi's, but it's Wumi for humanoid robots. So they basically have a arms and dexterous hand, exoskeletons about dexterous hand, and also have a cameras as the egocentric views. And the humans can use those to collect data and just use those data to train humanoid robots. So in this method, they won't have like a physical robot to teleoperate, just using humans to collect the data. I believe that will be a more scalable ways, and I think we will spend more time in the future on these topics. Yeah.
Right. Perfect. Yeah. Maybe I guess I think we are about to wrap up here. Maybe as a typical last question, Chris and I like to ask this: like, is there any cool paper you guys came across recently? You want to give a shout out to? Doesn't have to be related to humanoid. In fact, it could be computer vision or whatever. Yeah. In case there are some gems that me and Chris or the listeners missed, they can go and read up that paper. Yeah, maybe Wang, you can go first.
Yeah. So as we mentioned at the beginning, the Sonic paper from NVIDIA is a good one. And I guess it's pretty similar to the Twister 2 paper in terms of the device they use. They use a Pico 2, I guess, to teleoperate the robot. That will unlock a lot of capabilities. And the other thing, as I mentioned at the beginning, which is not a paper, is Unitree's teleoperation system, which was released last week. That was very impressive because I think they use some motion tracking system to do multi-person tracking, and then they do multi-person like a teleoperation with mocap system. So that one is also quite powerful. So I'm imagining in the future, if we can have a mocap system that is mounted in a very large space on the ceiling, and that can track multiple persons, then we can probably do some multi-robot teleoperation to perform an even harder task. So that one is very impressive. Yeah, those are some interesting papers. And the other interesting paper is I just want to give a shout to Jiageng. So he released a paper called Phase Word, which is trying to leverage some video generation model to generate some demonstrations and then transfer those demonstrations from a general video domain to the robotic domain, which is a very interesting one from my perspective.
What's it called?
It's called
What's it called?
Face Word.
Okay,
Okay,
cool,
great.
cool, cool. All right.
So we also have some, basically we're doing zero-shot robotic manipulations. That means we do robot manipulation without any robotic data for trainings. And so where data is coming from a video generators. So basically you are given an image and a task prompt and using video generators to generate like the process of how the task was completed. But it is only from the pixel space. The instructions are only from pixel space. And our work is we're trying to simultaneously reconstructing the underlying interactable scenes from the image and videos. And on top of these scenes, we can do the reinforcement learning to track the signals from the generated videos so that we can do the zero-shot manipulations. And also it's very generalizable without any robot data for training. So it is a basic idea of this paper. And we also have a very cool interactable demos. It's running on the web-based module codes. So you can just click on the interactive demos and you can play with that. I think it's a very cool demos.
Yeah, I'm looking at the website.
Very
Looks
cool.
super cool, man.
Yeah, we'll have to take a look. Maybe we'll
Cool.
you
Very
can come
cool.
back sometime.
Yeah. Yeah. Maybe how about Xiawei and Hongyi and any cool paper and Zhenyu?
Yeah. So yeah, like Yuan mentioned, I think for the data teleoperation pipeline, I think Twist 2 is very impressive, and I think it's control of the whole, like mimicking the human body movement. I think it's really cool, and we want to maybe do some improvements on it in the future, like introducing some dexterous manipulation, wearing some meniscus gloves or something like that, to do the some dexterous manipulation based on this whole body data collection pipeline. And also I think another interesting paper for me is the heater, the Unitree G1 playing ping pong. And I think that's also another impressive work for me. And that the humanoids doing sports. And I think we also want to do some fancy things like fancy sports like that using G1 in the future. Yeah.
That was actually the
Yeah,
last episode we published.
Yeah, we just published. He was here, last
But
month.
yes, that was a
talking
great
about it.
paper.
Super,
That was a,
yeah, that was super
Yeah.
cool. I guess Xiawei and Zhenyu.
Like the Twist 2, the Twist 2 paper. I think, one of the collaborators also in our lab, Zhao. I think it'd be cool if you.
Cool. And then Xiawei.
Zhenyu, is everything okay where you are? It's been like nonstop sirens.
Sorry about that.
No worries. Yeah, it's good.
Yeah. So for me, I also read the hitter, the ping pong one paper. I thought that was really interesting to me because, as I remember, I think they use like a third view camera for calculating the where the ping pong ball would land. Yeah, I thought that was a very smart approach, and I thought that, and me and Hongyi and Zhenyu also discussed that maybe in the future we might we are planning on doing something that's more egocentric based, so that we don't need a third view camera, and we would like to do some interactive tasks or a multi-robot task with egocentric camera. So that would definitely leverage the difficulty, but it would be really impressive if we are able to do that. Yeah.
Well, hopefully the G2 if it comes out, will have an actuated neck. It will make things a lot easier to do egocentric. It's a lot harder if your neck can't move. But anyway,
just,
I mean,
wider field of view cameras, honestly, like anything you could do.
put a 360.
Lots of stuff you could do better.
Maybe. Yeah. But yeah, anyway, thank you so much for coming on, guys. And also, I just want to give you guys credit for putting so much work. I know it's incredibly hard to even get this amount of data out there. I was a bit shocked, to be honest. like oh my gosh, how many robots do you bring in the process to get it? But thanks for putting it out there. I think the community will benefit a lot. And clearly, you guys did the ablation study. It will move the needle. So, yeah, thank you so much for the work. Well, looking forward to more papers from you guys.
Thank you so much for giving us the opportunity to share the.
For sure.
Cool.
Okay,
Yeah.
cool. See you guys soon.